from the meeting, please just try to join in again, because the recording has whatever deal guys has got you out of the meeting. So please try to log in again if you've been dropped out. So the duality theorem is a theorem that is used mainly to try and simplify the coding effort that you might have when you are dealing with computer solutions of field problems. So it relates to the interchangeability of the electric and magnetic fields, the electric current and charges or material properties in the two Curl equations of Maxwell's equations, that is the Faraday's law of induction and Ampere's circuit law. And we can actually obtain each of the laws, that is Faraday's laws or Ampere's laws, from each other by just making these substitutions. So in Ampere's law, or in Ampere's circuit law, all we need to do is to change the current density J to a magnetic current density M. But remember, this current density, the magnetic current density in volts per meter, it's not a real current, it's just a fictitious current that is usually applied so that we can make the Maxwell's equations look symmetrical. Usually once you solve, any values you get for M will be dropped off. So if you make in the Ampere circuit law, just make the J, I'll give you 1 minute, okay? And you go with me. Just write down Ampere circuit law, that is the curl of H is given by the current density J plus the displacement current density, which is epsilon, multiplied by D, the ddt of E. Okay? So once you have that, just change the J, okay, on a different line, change the J to M. The E that you have, you change it to an H, and the H, you change it to a minus E, and the epsilon, you change it to mu. Then simplify and announce what it is you get. Did you get the task?
Yes.
Yeah, what, have you obtained anything that looks familiar? Did you get the Faraday's law or you didn't?
Yes, we get it.
Yeah, so you get the Faraday's law from the Ampere's law, and usually for the in the Faraday's law, if you were to make the substitution M going to minus J, E going to H, and H going to minus E, and mu going to epsilon, then you'll obtain the Ampere circuit law. This is usually useful because now all you have to do when you're writing a computer program, you can only program one of the equations, and then you make it a routine or a function that you call. And the only thing you have to do is to make the calling variables that you call with just make the substitutions that we have talked about, and you'll get the same, you can use the same code to solve the problem. And remember that M will always be a fictitious kind of current and can be ignored after you get the solutions. So the duality theorem helps simplify formulation and computation of effort in computer-based solutions. Now, another theory that is important is, you must have met it in electrostatics, and you call it the theory of virtual image sources. This is usually best handled when we have looked at reflections, but I'm going to give a rough idea of what it is we are talking about. Then maybe when we get time in there, when we are looking at reflections and boundaries, we can look at it again and apply. So what you can take from here is that if an electromagnetic field meets a boundary that has different properties, then it won't continue moving in the same direction it was going. It may be reflected back into the region where it was coming from, or it change its direction as well. So a common problem in the electromagnetic theory will always involve a current source that is placed in the vicinity of a grounded conducting plane. That is, you may have a wire above a grounded plane or a conducting plane that is connected to Earth, so to speak. So image theory then allows us to remove that ground plane using what we call the virtual image source, placed an equal distance behind the ground plane itself. It's more like when you look at yourself in the mirror. If you are in front of the mirror a distance, say x, then your image, when it's a true image, it will be at -x behind the mirror. And what we are saying is that we can look at you guys together without the mirror by using these virtual image sources. So the orientation of the image source will be chosen such that the boundary conditions at the location of the ground plane are preserved. We know that the tangential component of the electric field intensity must be 0 on a conducting surface. And therefore, the image current source that will make behind the ground plane must be in such a way that it generates an electric field that is opposite the tangential component of the actual electric field due to the actual source, so that when we add the two by superposition, they add up to 0 at the position or the location where the ground plane was in the first place. And that will not violate any issues that, or any conditions that we had before. So we consider an x-directed current sheet of strength Js given by x cap J naught. And we assume that it's of infinite spatial extent in the xy plane. That is coming out and going out. It's actually infinite, so to speak. Okay, and thin in the z direction. So our current sheet has Js, and it's a distance L from the image, from the ground plane. And what we are saying is that we can replace the ground plane, we remove it, and we put in a current source that is in the opposite direction as J of S, okay? So that the E field generated at Z equal to 0 is equal to 0, so to speak. So the current sheet will be placed parallel to the ground plane at a distance L from the ground plane as shown in that figure. Now, because the current density is of infinite spatial extent in the xy plane, it will excite plane waves that will be traveling outward from it. One traveling backwards towards the ground plane, and one traveling forward towards the positive z infinity, so to speak. The backward traveling wave will be reflected in the ground plane at z equal to 0, and then will start to travel again towards the Z in the Z direction. Now the field distribution will correspond to that of a standing wave in the region between the current sheet and the ground plane, because we have both a forward moving wave and a backward moving wave. When we add the two, we'll have regions where the two waves reinforce and planes where they completely interfere with each other destructively. So the wave will not be propagating, but will be standing in place, oscillating in the spatial direction. A propagating wave will be generated in the region Z beyond the current sheet, that is at Z greater than L. Now, because the current induced in the ground plane is along the X direction, the tangential components of the electric field intensity associated with the waves must be in the X directions as well, because the current density is pushed by an electric field. And therefore, in the region 0, between the ground plane and the current sheet, we can write for the electric field that will have a forward moving wave or a field component plus a backward moving wave component. That's why we have exponent of jkz and exponent of minus jkz in that form. And both of them are in the X direction, so to speak. Now, because the tangential component of the electric field intensity must vanish at the ground plane, then we must have that the two amplitudes, and when we replace Z by Z equal to 0 at the ground plane, we should have that Es minus, that is the amplitude of the backward moving wave, must be equal to the negative of the amplitude of the forward moving wave component. Or in other words, we can just drop out the plus and S and put it as a minus E naught, where E naught is a general amplitude of the electric field intensity in this region. And therefore, we can write that for between the whatever the Z equal to 0 and Z equals to L region, we therefore have that the electric field intensity ES is going to be given by that equation there, and we see that this is just the negative of J of 2 E naught and the sine of Kz. It will be 0 at Z equal to 0, okay? And we can see that this is a true solution for that. The magnetic field intensity is of course given by the direction of propagation unit vector cross the electric field. And we can see that this is going to be given by that equation there. And we see that the value is just going to be given by the X cap. Okay, the direction vector for the backward moving is of course minus Z. That's why we are putting here a minus, while that it's positive Z for the forward moving. And that's why I've taken out the minus out. And therefore we see that it's the H field is in the positive Y direction, and it has two components as well. And we can see that this is just going to be given by Y cap E 2E by eta and multiplied by the cosine K of Z. This K naught, of course, is the K I'm dealing with, and I just must have not removed the values of the K naughts here. I wanted to use the K rather than K naught. Now, in the region Z greater than L, only the forward moving, forward propagating wave exists, and it may consist of a direct wave generated by the current sheet or a component reflected, the component reflected from the ground plane. But this should not be part of it because it can't go through the current source anyway. Okay, we can always ignore this. And therefore, what we can do is that we can write that the forward moving electric field intensity is going to be given by an amplitude E plus exponent of minus jkz, and the magnetic field intensity is that value divided by eta equal to times the exponent of minus jkz. That is, It's going to be given by the z cap cross E and divided by eta, where you recall eta was called the intrinsic wave impedance of the medium through which the wave is propagated. And therefore E plus is just a resultant electric field intensity amplitude. It may have other contributions, but this is what it's going to be. And we are going to try and see how they relate with the others, the E naught that we found before. So continuity of the tangential component of the electric field intensity at Z equal to L requires that the amplitude of the standing wave must be equal to the to the amplitude of the forward moving wave at Z equal to L. Or in other words, if we were to replace Z by L, then we'll get that the E naught sine KL must be given by E plus the exponent of minus JKL. And therefore we can relate E plus in terms of E naught as the minus of J 2 epsilon E naught sine KL and multiplied by the exponent of J, K, and L. The magnetic field intensity is of course discontinuous at Z, and we say that the discontinuity at that L is going to be the amount of J, or the amplitude of the current sheet that we have, and that we saw was going to be J naught. And therefore, we can write that if we take the tangential component of H of Z at Z equal to L, we'll just get X cap J naught. Or in other words, we can write that this value is going to be given by that equation there, E naught by eta cos KL, that is plus the J2 E naught by eta sine KL, and this must be equal to J naught. Therefore, we can write E naught in terms of the current density amplitude J naught as shown below, where we see that the cosine of KL plus J sine KL is simply the exponent of JKL. And therefore, if we can see that E naught is just going to be given by eta J naught by 2 multiplied by the exponent of minus JKL, that is divided by that equation there. And therefore, E plus is going to be given by minus J eta J naught sine KL, and in the region 0 between the position of the ground plane and the current sheet, you can therefore write the values of the field are going to be given by that value, and the value of the magnetic field is going to be given by that equation there. And in the region beyond the current sheet, the equations are shown. Now, this has not used what we are calling the image sources. All we want to show is that once we use the image theory, we'll get similar equations. So you keep these expressions in mind, because this is what we want to prove now that we can obtain when we use the image theory. Now, the image theory solution is depicted here. All we are saying is that we remove, since the current, this current here will have an E that is pushing it towards the X direction in the ground plane, okay? Therefore, for this E field going in the X direction to be 0 at this point, we must have another current sheet at this point that generates an E field at Z equal to 0 that is opposite that being pushed by this electric field due to this current source. And that's why we have a minus Js going in the opposite direction. So the current sheet, Js, is going to be given by the minus of x J naught at Z equal to minus L, which will establish a wave that we are going to call E1. One will be continuing in the negative Z direction, and another one will be propagating in the positive Z direction, and it will arrive, it will it will have to move L first before it gets to Z equal to 0. And that's why we have minus JK Z plus L. And then here we have a value of the backward moving, which is JK Z plus L at that point. So that at the position of the current sheet, this Z plus L is equal to 0 here and is equal to 0 there as well. So that we are at exactly at the minus L. And the magnetic field H1 will be given likewise in that form. The actual current sheet that we started with at Z equals to L will establish itself a wave that is E2 with a component going in the positive Z direction and a component moving in the negative Z direction, as well as the magnetic field. And again, we see that at the position of the current sheet, we want that this argument be equal to 0. So we have Z minus L, so that when we put Z equal to L, we get a 0 here at the current sheet. And therefore, in the region between minus L, Z, and L, we therefore have two waves. The wave component, due to the image current source moving in the positive Z direction, plus the image plus the backward moving component of the wave generated by the actual current source at Z equal to L. And for the magnetic field intensity as well, we get that kind of equation there. So boundary conditions at Z equal to 0 require that the field E vanish, that it must go to 0, and therefore it only means that the exponent or E1 plus exponent of minus JKL plus E2 minus exponent of minus JKL must be equal to 0, or in other words, the E2 minus must be equal to the negative of E1 plus. And therefore, once we use those equations, those values, we see that E is just going to be given by minus J x cap 2 E1 plus exponent of minus JKL sine KZ, just like we had before. And the H will be given by that equation with the exponent of minus JKL, the cosine of KZ. Before, of course, we didn't have this value, but now we are already expressing the actual amplitude that we got before. So in the region beyond the Z equal to L, we have E is going to be given by E plus exponent of that, and H equal to E plus eta over eta, and multiplied by that equation there. And the continuity of E at Z equals to L then requires that equation sine KL be equal to that amplitude we are dealing with here. And the discontinuity of H at Z equal to L requires that equation plus that equation must be equal to the actual current source that we have there as J naught. Or in other words, we can see that again we have a similar equation as before, and you can see that E1 is just going to be given by eta J naught by 2. And therefore, in the region between Z equal to 0 and Z equal to L, you can write that equation as that, and the magnetic field given as that, just like we got before. In the region beyond, we have that equation given by that value, and we can always express this out, that is, we can spread this out, and we'll see that this equation becomes the sign of that value there. And H is going to be given by that equation as well. And therefore, we see that the equations are the same as before, and we have now proved that we can use image source theory to solve the problems that we have. This is very important, especially when we'll be solving certain field problems, such as would be found when we are dealing with antenna. Okay, many of the antennas will be radiating above a ground plane, and we can solve the problem as the antenna in isolation, and then We use two antennas, one which is an image and one which is the actual antenna, and we can solve the problem and require that the only field that is true will be that one beyond the ground plane. So for example, in this particular case, the only field that we are interested in is the field beyond z equal to 0. The one which is towards the minus L side, that one is not a true field for us in the actual situation. So any solutions that we get for z less than 0 will be ignored in our solutions, and we just take only the fields that are beyond the ground plane. Okay? So what we can illustrate now is some of the situations that you are going to meet in many cases when you are dealing with stuff. And most of them are usually the magnetic fields and the electric currents and the magnetic currents. With that, we look at now what we call the wave polarization. But with that, I'll give you a 3-minute kind of break to try and look back on, reflect on what we have just talked about. Remember, the image theory is going to become much more understandable once we look at the reflection or the wave behavior at boundaries or medium boundaries. Usually in a face-to-face lecture, I would leave it to that level, but since I put them together here, that's why I've given it as well. So just a few minutes to think about that. So if you have any question, you can always ask. I'll be ready to, I'll try to see whether I can resolve any issues that you may have. So there being no questions, then we are going to continue now, and we look at what we call wave polarization. Remember, we talked about the dielectric polarization, whereby application of an electric field distorted the charge distribution around the molecules making up the dielectric, and therefore the molecules are induced electric or dipole. If we had a magnetic material, we would also have the domains in the magnetic material orienting themselves with the applied field, and therefore we'll have a magnetic polarization as well. Now, one important thing we should realize is that now when we talk about wave polarization, and it was going to be a different concept as compared to the material polarization. And many times when we ask questions such as this, you'll find someone using wave polarization when you want to mean material polarization or vice versa. So by wave polarization, all we are trying to say is that is the temporal behavior, that is, how does the vector field or the E field vector behave in space, a given point in space as time progresses. That is, if you are standing somewhere by the side and you are watching or looking at the wave as it's propagating away from you or towards you, how would the vector or the E vector be behaving in space? The general one is where it will be describing ellipse in space, okay, for this plane wave, so to speak. So we consider a plane wave that is traveling in the positive Z direction as shown in this figure here. Well, the wave is coming directly at us, and therefore we are just seeing the point or the tip of the arrowhead that shows the direction of propagation. Now, if the E field is oscillating in the y and minus y direction, we are saying that it has a field or an amplitude E2, then we say that this field is linearly polarized in the y direction. The E does not have an x component. So the electric field intensity vector therefore points in the y direction at all times, and therefore the wave will be described as linearly polarized in the y direction, or we can equivalently call it a y-polarized wave. The electric field intensity may then be expressed as Ey equal to E naught or E2 multiplied by the exponent of j omega t minus kz. The j should be actually outside these brackets, so that it's, or I should write j omega t minus j kz. This is a mistake I'll correct before I send you the slides. So in general, the electric field may have an x component as well, and the two components may have an equal amplitudes and phase relative to each other. Okay? So the wave will therefore be described as elliptically polarized and would be illustrated as shown below, where we have E2 greater than E1, and therefore we have an ellipse that is oriented vertically or towards the y direction, so to speak. That is, the major axis is in the y direction, while the minor axis is in the x direction. But in the most general case is where E1 or the EX and EY have a time phase difference, okay? And when they have a time phase difference, the ellipse will be tilted with respect to the x-axis. So at a fixed point, at a fixed z, the electric field vector then is seen to rotate as a function of time with the terminals describing an ellipse that we shall call the polarization ellipse. The polarization ellipse of a given wave will be characterized through the ratio of the major to the minor axis, and this is usually given the value or the symbol or the name axial ratio, or AR, or in other words, AR is defined as E2 divided by E1, where E1 is of course the amplitude of the x component and E2 is the amplitude of the y component, and therefore for a y polarized wave, we shall see that AR is going to be infinite. And for a next polarized wave, we just get AR equal to 0. So if E1 and E2 are equal, then the ellipse reduces to a circle, and AR is therefore unity, and the wave will be described as a circularly polarized wave. Linear and circular polarizations can therefore be seen to be special cases of the elliptical polarization, because for circular polarization we need the amplitudes of the component to be equal, while for linear polarization we require one of the component to disappear or to have no phase difference, time phase difference, so to speak. In the most general case, the polarization ellipse may be oriented in any direction in the xy plane, depending on the phase relationship between the E1 and E2. By phase relationship, I'm talking about the time phase, that is the omega t as we move around. And therefore we can write that Ex is going to be given by the E1, the cosine of omega t minus kz, while Ey is given by E2, the cosine of omega t plus an angle theta, which we are saying this angle theta is the phase difference between Ey and Ex, minus the propagation, the spatial propagation phase factor kz. So theta is the phase angle by which Ey then leads Ex. The resultant electric field intensity is therefore going to be given by the vector sum of the x component and the y component. And the y component can be expanded in the trigonometric expansion. You can expand it as the cosine of omega t minus kz multiplied by the cosine of theta, and as the sine of omega t minus kz and the sine of theta. Now, if we were to check, we say that we are looking at the wave at a given position z, and with no loss of generality, we can always assume that we are looking at the wave or at our position, which we take as the reference, and we say that the z is going to be equal to 0 at that time. And if we put z equal to 0 in the equations for Ex and Ey, we see that Ex is equal to E1 cos omega t, and Ey is going to be given by E2 cos omega t cos theta sine omega t sine theta. And therefore we can express cos omega t in terms of Ex and E1 and write it as cos omega t is given by Ex divided by E1. And therefore, since the sine omega t is just the square root of 1 minus cosine squared omega t, we can see that sine omega t is going to be given by the root of 1 minus the Ex by E1 all squared. And therefore, we are going to use this in the expression for y, for Ey, and we see that it means that Ey by E2 minus Ex by E1 multiplied by the cosine of theta must be equal to the minus of sine theta multiplied by the square root of 1 minus Ex by E1 all squared, which this is sine omega t, so to speak. And this doesn't look very nice, so to remove the square roots, all we need to do is just to square the whole of both sides of the equation, and we get the following. But ey by e2 all squared minus twice ex e1 ey e2 cos theta plus ex by e1 all squared must be equal to sine squared theta. All we have done is to take this value. It will be sine ex e1 all squared sine squared theta, and we take it to this other side, and it will cancel with the e1 ex e1 all cosine all squared. So we'll see an ex e1 all squared into sine squared theta plus cos squared theta, and therefore this just remains as that. So this equation is usually expressed in the form A of ex squared minus b of ex y and ex and ey plus c ey squared equal to unity, where the A are defined as shown. And this equation is an equation of an ellipse, okay? A mathematical equation for an ellipse in the whatever the locus itself. So the equation describes an ellipse that will be tilted at an angle tau given by the arctangent of E2 by E1 relative to the x-axis as shown here. So the major axis is that value there, and the minor axis is that, and tau is where the major axis, the angle made by the major axis with respect to the x direction. And this is a general elliptic polarization case. The polarization state of a wave is specified through the parameters of the polarization ellipse. And thus, we have one, linear polarization in the x or y direction if E1 is not equal to 0 and E2 is equal to 0, or E1 is equal to 0 and E2 is not equal to 0. We can also have E1 and E2, okay, being not equal to 0, but with theta equal to 0. And in that case, we'll have a linear polarization with a tilt angle. That is, we can have tau equal to pi by 4 if theta is equal to 0 and E1 is equal to E2, but not equal to 0 itself. Circular polarization will occur if E1 and E2 are equal and theta is either plus or minus 90 degrees. We define left-hand circular polarization if theta is equal to positive pi by 2, and right-hand circular polarization if theta is minus pi by 2. By left-hand and circular polarization is to look at how the vector is rotating in space or in the plane as time progresses. If it goes anti-clockwise, it will be called right-hand circular polarization. If it goes clockwise, it will be called left-hand circular polarization. We shall see that this is there is an ambiguity because the direction of rotation depends on whether the wave is moving away from the observer or the wave is coming towards the observer. So left and right hand circular polarization can be understood by examining the time evolution of the electric field vector at z equal to 0. Now, if we consider a wave with an EY that is leading EX by theta equal to 90 degrees, then at omega equal to 0, okay, E is going to be given by X cap of E1. And at omega equal to 90 degrees, it will be in the minus Y direction. And therefore, the electric field vector would be seen to be rotating clockwise as the wave approaches the observer. If the wave were viewed receding from the observer, okay, however, the rotation would appear to be counterclockwise, and therefore the IEEE definition is the following, that if the electric field of an approaching wave is rotating in the clockwise direction, as time evolves, the wave will be described as being left circularly polarized. And this is in opposite is an opposite definition as what will be used in by the physicists or in classical optics. So the clockwise or counterclockwise rotation will depend on the direction from which the wave is observed, and therefore the polarization state of the wave described by the IEEE definition is ambiguous. The ambiguity will be removed always by using the characteristic of some antenna we call a helix. A helix is just like a coil, okay, that is open, and it depends, like the screws that you meet in mechanical engineering. We have a right-handed screw and a left-handed screw, or the right-hand rule and left-hand rule kind of thing. And therefore, we'll see that a right-handed helical antenna will only radiate and receive right circularly polarized waves, okay, as defined by the IEEE. The left-handed helical antenna will radiate and receive only left circularly polarized wave. And therefore, we can always remove that kind of ambiguity in the state of polarization of the wave. Okay? So, like the right-handedness of the helix is just like the right-handedness of the screw, and it does not depend on the position from which you are viewing it. So, an example. What we want to show is that these equations, or these circular, elliptic, and linear polarizations are actually can be obtained from each other. So the example here is to demonstrate how we can obtain circular and elliptic wave polarization in electromagnetic waves. So we consider a superposition, a wave that is a superposition of two linearly polarized waves. One wave has an electric field component EX, and the other has an electric field EY, lagging EX by 90 degrees in time phase. That is, one wave component has only EX, so it's X polarized. The other one has only EY, so it's EY polarized. But the EY component has 90 degrees, lags the EX by 90 degrees. And therefore, the electric field intensity phasor will therefore be the vector sum of the X cap EX and the Y cap EY. And we see that this is going to be given by EX. Because it's lagging, therefore it has to be minus J, where minus J is, of course, the exponent of minus J pi by 2. Okay? So to show that time lag of EY with respect to EX. So E1 and E2 are, of course, the amplitudes of the two linearly polarized waves. So once we have that, we can see that the instantaneous expression for E is then going to be given by its phasor value multiplied by the exponent of J omega t, and we take the real part thereof. And we see that the X component will have E1 cos omega t minus Kz plus J E2 cos omega t minus Kz minus pi by 2, as we had before. And therefore, at a given point in space, E will be changing its direction with time. Now, if we recall that at Z equal to 0, the E of 0 at t is just that E1 cos omega t plus sin omega t, then we can see that as omega increases from 0, okay, the tip of E will be describing a closed path in a counterclockwise direction. Analytically, you can write that E cos omega t is given by that EX0 of t by E1, and sin omega t is equal to EY0 t of E2, and we can see that is the square root of 1 minus cos squared omega t. And therefore, we can see that that equation is going to be given by that, and therefore we can see that E1 will be elliptically polarized if E2 is not equal to E1. This is like saying x squared plus y squared equal to r squared, or something like that. And we can see that depending on how they are related, it would be an ellipse or a circle, so to speak. Now, if we look at a circular polarization circuit, or consider the whatever situation here, and we are seeing that this value here is that the omega is going counterclockwise. It's increasing in that direction as time evolves. And therefore, we want to see the angle alpha made by the E phasor vector with the x-axis. So, if E2 is equal to E1, the instantaneous angle alpha between E and the x-axis at z equal to 0 will be given by alpha equals to arctan of EY over EX. And we see that that is just going to be given by omega t. And therefore, E will be rotating at constant angular frequency omega in a counterclockwise direction. And this is what we describe as right hand or positive circular polarization. And if we were to note that we use the fingers of the right hand, okay, and make them follow the direction of rotation of E, the thumb will be pointing in the direction of wave propagation. Okay, and this describes the right hand or positive circularly polarized wave. Okay, using your right hand rule, so to speak. And if EY leads is EX by pi in time phase, you can have that is the value that we'll have for the phasor, and we have left hand or negative circularly polarized wave in this particular case. If EY or EX is 0, then we have the linear polarization. So in many cases, when you will be dealing, if you are employed by a radio company such as Kiss FM or the KBC and so forth, when you are using amplitude modulation broadcast, you'll be using linearly polarized signals, and with the E usually normal to ground. That is, we can call it a vertical linear polarization. FM or frequency modulation signals usually use circular polarization, while TV will use linear polarization. Okay, in the sound of, I think in the picture, the sound is usually FM modulated. The picture will be either AM modulated, and the E will be parallel to the ground. That is horizontal linear polarization. And if you look at the antennas that you see on buildings, in the houses, you see that the antenna is actually parallel to the ground. It's usually placed with the rods or the elements parallel to the ground or horizontal, in the horizontal direction. If you looked at police communication antennas, they look just like those ones of the TVs that we use in the house, but they are mounted vertically. It's because most of the police communications and the like, they are using AM broadcast, and they use the vertical polarization mainly. So it means the police signal cannot be received by your television antenna because the polarizations are not the same. Okay, and therefore will generate no signal there, and there will be no interference. So this is what we usually call whatever the orthogonal polarizations, and it will be used mainly in communication systems to try and reduce interference. So example 2, we are required to prove that a linearly polarized plane wave can be expressed as a superposition of a right-handed and a left-handed circular polarized wave components, which are of equal amplitude. So what you need to do for that is just to consider a linearly polarized plane wave as propagating in the z direction. This is, you can use negative z direction if you like, or positive or positive y and so forth. You have E naught exponent of minus jkz. Now, what I propose is that we can always express Ez in the following form: a component that is right circularly polarized plus a component that is left circularly polarized. And once we use that, the definition of ERC and ELC, we can write that ERC is going to be given by E naught divided by 2, because we want in the end the amplitudes to be E naught. So it's going to be E naught by 2 x cap minus j, that is the y is lagging the x component by 90 degrees, exponent of minus jkz. And ELC is going to be given by E naught by 2 x cap, and the y component leads the x component by 90 degrees, and then multiply by the exponent of that. And therefore, if we added these two, we'll see that all we'll be left with is the x component alone, because then the y components will cancel out because of the difference in them. One is minus, the other one is positive. And we get our linearly polarized wave is given clearly. Usually, such a question may be asked, and we'll find that many of us will be going to try and compute so many things, and the only thing we are required to do is just to make a simple kind of substitution or kind of approach. Now, if we have an elliptically polarized electromagnetic wave, how would be the Poynting's vector look like? And remember, the Poynting's vector we said is related to the rate at which power or energy is being transmitted or propagated by the wave away from through a surface. So the complex Poynting's vector was defined as P equal to E cross complex conjugate of H. And the time average Poynting's vector was then given as the real part, half the real part of the complex Poynting vector as P average equal to half the real part of that. And we saw that that is just a half of the real part of E cross H star. Now, suppose the wave that we are dealing with is elliptically polarized, so it has X component and Y components of an equal amplitudes. We have Ex equal to E1 exponent of j omega t minus kz. Ey is equal to E2 exponent of j omega t plus theta, where theta is the angle by which Ey leads Ex minus kz. Remember, when the associated magnetic fields are going to be Hy associated with Ex and Ey and Hx associated with Ey. So at z equal to 0, the actual phasor, electric field intensity phasor, is going to be given by that equation. Okay, and the associated magnetic field is given by Hy equal to H1 exponent of j omega t minus phi minus kz. Phi is the angle by which the magnetic field is ahead of the X component of the E field, or the X of the E field that is dealing with it, so to speak. Okay, that is the time phase of H relative to E. Similarly, the magnetic field associated with Ey is going to be given by Hx equal to H2 exponent of j omega t minus phi plus theta minus kz. And hence, we have that H is going to be given by that vector sum, and we can see that the P average is going to be given by a half of that, and what we get is Ex, Ey, Hy, Ey, Hx, and once we substitute the values that we have there, we just get that the theta falls out, that is the angle by which Ey leads Ex does not affect what the value of P average is going to be, but the angle by the phase angle by which H, or the magnetic field, is out of phase with respect to the E, will come in. And this is the beginning of what you get in power systems, where you call the cos phi, or the cos factor, or the power factor of the power that you are dealing with. And therefore, we can say that P average is independent of the phase angle between X and Y components of E, and only depends on the power factor. So from the solutions of the wave equation, H and E are related as Ex by Hy equal to minus Ey by Hx, and is equal to the intrinsic impedance of the medium. And therefore, P average is just going to be given by that value. And we can always express it in terms of a value for H, which we are calling that it's the X component plus the Y component squared, taking the square root is the magnitude of the magnetic field vector. And also, we could also use the values for E, and we have that the actual E, my amplitude, is just the square root of E1 squared plus E2 squared, or the X component squared plus the Y component squared. And we see that those are the values that we get for that particular case. So another example is to look at the elliptically polarized wave that is propagating in the positive Z direction in air and has X and Y components of the electric field vector given as shown there. That is Ex is equal to 3 sine omega t minus Kz, and Ey is equal to 6 sine omega t minus Kz, and it's at 75 degrees with respect to Ex, all in volts per meter. And what we are required to do is to determine the average power per unit area transported by the wave. Electromagnetic field or the electrodynamic field problems, you will be asked average power or something like that. Remember, anytime you are asked about average power or average power per unit area or power density, all that is required, or all you are required to remember, is that that is given by the average of the pointing vector. The average pointing vector will give you that value of power per unit area. And that's all you are being asked, to derive or to evaluate the pointing vector average. So, as a solution is that we consider the magnitude of that pointing, the average pointing vector is going to be given by a half of Ex, the amplitude squared of Ex, amplitude squared of Ey, and divided by eta. And we can put those ones immediately into the equation, and we get something like 60 milliwatt per meter square. Okay, there's nothing else to do with it. Now, sometimes you can get the E field rotating in a plane that is parallel to the direction of propagation. Once you get that, you get what you call a cross field. Cross fields are usually not very nice, especially they'll appear especially when you are dealing with what we call antenna arrays, and they usually introduce a distortion in their signals, and the characteristic of your antenna array will also be compromised. So the cross field condition is not possible when you have only one wave, a plane wave that is propagating through space, because there's nothing to interfere with it. But there are several ways in which they can have. Okay, a plane wave we saw, it's purely TEM. It has no axial field component, that is, there's no EZ or HZ. It has only the transverse electric and the transverse magnetic field intensity components only. And therefore, cross field is not possible. We can get cross fields conditions when, one, we are looking at the near field of an antenna. That is, if we look at the field that is being radiated very close to the antenna, and a cross field condition may occur. If we have a wave or a plane wave that is propagating in a parallel to a surface, a conducting surface, it may, because there is no conductor that is perfect, will have at least an EZ generated inside the conductor that will push the surface current density or support the surface current density on that conductor. And therefore, we introduce an EZ, and therefore it's possible for the electric field intensity to rotate in a parallel direction or parallel to that surface. Another, in general, the cross field condition will occur whenever two waves of equal frequency, such as an incident and reflected wave, live near the a conducting surface. This can interfere and cause the cross field condition. Okay, this is what we are saying. That is, the incident wave is approaching the conducting plane at an oblique angle of incidence. Okay, and the electric field the fields of the incident wave and those of the reflected wave may cross near the conducting surface and introduce that kind of cross field condition. Another way of dealing with the polarization is to use what we call a polarization ellipse or a Poincare sphere. Okay, this I'll give only as for completeness. Usually we don't test this at our level. Our level of polarization is already done with what we have already looked at. But so the polarization state can be taken as a point on a sphere, okay, where the longitude and the latitude of the point are related to the polarization ellipse parameters, as the longitude will be given by twice the tilt angle, and the latitude will be given by twice epsilon, and we shall show what the epsilon is about. So tau is the tilt angle lying between 0 and pi, and epsilon lies in the range pi, and that, and it's related to the axial ratio of the ellipse. Okay, so epsilon is the arc cotangent, okay, of the minus or plus of AR, where the negative value of AR is from IEEE definition. Its AR is less than 0, is negative when we have right-handed polarization, and positive for left-handed polarization in that case. So the polarization state is then specified in terms of the angle subtended by the great circle that will be drawn from a reference point on the equator, okay, passing through the point that we are dealing with. A great circle, remember a great circle from your friends from survey and photogrammetry. A great circle is the circle on a sphere centered at the origin of that sphere. That is, its point, its origin is at the center. And therefore, if you look at the latitudes on the Earth's globe are not great circles, but meridians or longitudes are all great circles on that sphere. Okay. When you are traveling by plane, usually the plane will be, the route of the plane will be defined such that it follows a great circle as much as possible, because any 2 points on a spherical surface, the shortest distance between them would be a part of a great circle. Okay, you can't just go around the way you just walk around on a plane surface, so to speak. If you follow the great circle, you'll be shortening the distance. So the angle between the great circle and the equator, which is theta, is also going to be part of that state. So this is how we define them. So the great circle passing through the point, this is our point here that we are dealing with. So the great circle has an angle of sigma, that twice gamma. Okay, that would be the angle with a reference point here. The angle between the great circle and the equator is theta, which you have given there. The twice epsilon is of course that angle there, and the tau, the tilt angle, is given as that twice tau there. So this is how the Poincare sphere looks like. The sphere, of course, will be a complete sphere where we have the North Pole and the South Pole, and both of them will introduce polarization states. So the relationship between tau, epsilon, and gamma to the polarization ellipse is shown there. And the great circle angle is twice gamma, and the equator great circle angle is theta. So from spherical trigonometry, the relationship between the angles is that, and the great circle half angle gamma then lies in the range between 0 and 90 degrees. The temporal phase difference between EX and EY is in the range of minus 180 degrees to 180 degrees. That is, you can have minus pi to pi. And therefore, knowing epsilon, tau, gamma, and theta, any of the parameter pairs will then be determined. The polarization state will then be specified through either a state M, epsilon and tau, or a state P, gamma and theta. So there are two special cases that are of interest, and one is when theta is equal to 0, or when theta is equal to plus or minus pi. We have EX and EY will either be in or out of phase, time phase, so to speak. And any point on the equator will represent polarization state of the wave. Polarization state will be linear in the x direction at the origin, okay? And when theta is equal to plus or minus 90 degrees and E1 equal to E2, we'll have twice gamma equal to pi by 2 or 90 degrees, twice epsilon equal to plus or minus pi by 2, and we have both EX and EY with equal magnitude, but they'll be in quadrature time phase. Therefore, the polarization state will be circular. So these two states represent limiting conditions for the polarization state of a wave, and any point on the northern hemisphere will describe a left elliptic polarization, and this will range from left circular polarization at the North Pole and linear polarization on the equator. Likewise, we have the southern hemisphere giving right elliptically polarized waves, and the complete Poincare in a two-dimensional map is as shown there, with the polarizations given to you with tilt angles as they keep on moving up towards the equator where we have linear polarization. So this is how you would represent that. Like I said, this is a drawing after Krauss and Kawa. So you can, if you want to learn more about that Poincare sphere, you can actually refer to that tome. So it can be shown that the voltage response of an antenna with a polarization state MA to a wave of arbitrary polarization state M is given by V equal to K multiplied by the cosine of MA, MMA, that angle, divided by 2, where this is the angle subtended by the great circle from the polarization state M to the polarization state MA. And M is the polarization state of the actual wave. MA polarization state of the antenna as given above, and this is defined with the antenna as radiating rather than receiving. So K is a constant that will depend on the field strength of the wave and the size of the antenna. We shall see when we deal with antennas next semester that the size of an antenna, the physical size may be different from its electrical size. So when the angle is 0, the antenna polarization and the wave polarizations are said to be matched, and therefore the response of that antenna is going to be maximum. If they are 180 degrees, the response will be 0 because the antenna and the wave are said to be completely mismatched. It's more like what we say, that you have an antenna that is vertically polarized, but the wave has the electric field parallel to the Earth's surface. That will not be received, and that's what we are talking about, mismatching the two, or orthogonal polarizations. And this could arise if the antenna is polarized in the X direction, say, while the wave polarization is in the Y direction. Or we have an antenna with a right circular polarization, while the wave is left circular polarization. So whenever this occurs, the antenna is usually described as blind to that wave, or it's blind to the wave of opposite or antipodal polarization states. And when you will be dealing with communication systems, that's what you'll be worrying about. Remember, we say that if we were using satellite polarization, there is what, as the electromagnetic wave goes through the ionosphere, which is the plasma we dealt with before, the electric field and the magnetic field in the wave will interact with the electric field in the ionosphere and the magnetic field of the Earth, and the wave will start to rotate, and the polarization state, if you are using a plane wave from the antenna on the satellite, then the polarization state on the ground will not be known which direction it is. And therefore, usually, it's much better to use a circularly polarized antenna at the ground, because then it will receive at least part of the signal that is coming through the waves, through the ionosphere, so to speak. That rotation is usually referred to as Faraday's rotation. But in many cases, we don't have complete polarization. Most of the waves, the resultant wave will have the E field pointing in any direction, so to speak. Such kind of waves are said to be unpolarized. And they would be the waves that would be coming from the sun, say, for example. So, when we have complete polarization, we can only have that when we have a monochromatic or single frequency waves, and this is very rare in many cases. So many celestial radio sources will be characterized by waves with a wide frequency range, and within the frequency band delta F, the wave will consist of a superposition of a large number of statistically different waves in a variety of polarization states. And therefore, the resultant wave will therefore be said to be incoherent or unpolarized. At a fixed point in space, the electric field intensity of an incoherent wave may be expressed as Ex given by an amplitude that is varying with respect to time and multiplied by the sine as a sinusoid, so to speak. And the Ey will have that with a phase that is also varying with time with respect to EFN. And all functions are then assumed to vary independently with time. That is, they are not synchronized, so to speak. The time variation of E1 and E2 and theta will be slow when compared to the average or the center frequency omega of the resultant field, and will generally be of the same order of amplitude as the or rate as the bandwidth of the wave. So a wave that has this kind of thing can be generated by two noise generators. That is, we can have two electrical generators or noise generators, then attached to an antenna, okay, or to antennas that are polarized in the X and Y direction. And then at the field point, if the two antennas have the same power at that point, the wave will be completely unpolarized. So one will be connected to the X polarized antenna, another to the Y polarized antenna, and the total wave will be unpolarized at the field point, so to speak. So the wave polarization will then be partial in general, and we can say that the resultant wave can be expressed as a superposition of one, a completely polarized component, and a completely unpolarized component. That is, we can have a part that is completely polarized, and we add on it a noise-like kind of component in terms of polarization. And such a state, okay, can then be described in terms of what we call the Stokes parameters, given as I, Q, U, and V, and they are defined as I is equal to, this is related to the Poynting vector, the complex Poynting vector. Although we've been using P, many people use S. So we are using this as the average, the complex pointing vector, which has an x component and a y component, and it will be given by 1 by eta naught. The eta naught is, of course, is because we are assuming free space, and it will be given by the expectation of E1 squared and the expectation of E2 squared. Because E1 and E2 are random variables, the only thing we can get is their average square value or the mean square value. And this is what we are representing by these expectation values. The Q is defined as the Sx minus Sy and given by 1 by eta of that minus the other. The U will represent the cross products, okay? And the V represent the sign cross product. So S will equal to Sx plus Sy will be the total time average power density, okay? Although we've been using P average like I alluded. So for a completely unpolarized wave, Sx and Sy are equal, and E1 and E2 are completely uncorrelated. That is, they are independent of each other. And under this condition, then the cross products must all go to 0. That is, when you are dealing with signal processing in telecoms, we'll be talking about cross correlation. They are completely uncorrelated, so the cross correlation is going to be equal to 0 for the two of them. So, and therefore I is going to be given by S, Q is going to be given by 0, U is equal to 0, and V equal to 0. For a completely polarized wave, E1, E2, theta, epsilon, and tau are constant, and the Stokes parameters will not require that we do a time averaging. Okay? And therefore E, for E linearly polarized in the x direction, say, and E2 equal to 0, that tau and epsilon are all 0. And therefore I is equal to S, Q is equal to S, U is equal to 0, and V is equal to 0. And if E is in the y direction, we have the opposite, that is Q is minus S. And therefore we can put, and for circularly polarized waves, E1 and E2 are equal, and theta is equal to pi by 2. And therefore we can have those equations as appearing there. Okay, so that's, in all cases, I is always equal to S, that is the total time average power density of the wave. Q is the time average power density of components in the x and y direction. And U is the time average power density of linearly polarized components at a tilt angle of tau equal to 45 or 135 degrees. And V is the time average power density of circularly polarized wave components. And therefore, the degree of polarization D will be defined as the ratio between the completely polarized parameter component over the total power. And we see that that is going to be the square root of Q squared, U squared plus V squared divided by the total, which is I. And this lies in the range 0 and 1. And because that value equal to I squared indicates complete polarization, then partial polarization will be the sum of a polarized and polarized part of that wave. And Stokes parameters may then be normalized to the total power of the wave, and we write them now as small numbers. And using the normalized parameters, we have them as S0, S1, S2, and S3 in matrix form. And we see that for the unpolarized component, we have that. The polarized component, we have that value there, where S0 is just I divided by S. S1 is equal to Q divided by S, and S2 equal to U over S. Remember, S was given as Sx plus Sy, and therefore I is just the value there, and we get the others as defined. And if we consider a wave with parameters S0, S1, S2, and S3 incident on an antenna with parameters A0, A1, A2, and A3, then the total power available from the antenna, the total power available is the maximum the antenna can give you under these conditions, and therefore due to the incident wave, it's going to be given by that multiplied by that value there. And if you look at this, you'll get that the half, that is going to be half. AE is usually called the antenna aperture or cross-section area, and this is usually an electrical kind of quantity with dimensions of area, but it's related to the wavelength of the signal. Therefore, A or P can be given by that value, and AE is called the effective aperture of the antenna, like I've alluded. Usually it has, it is a function of the signal wavelength, okay, rather than the antenna dimensions. S is the time average power density, or the P average that we've been dealing with. And MMA is, of course, what we had before, is the angle, okay, between the polarization states of the wave and the antenna. And therefore, in this particular case, if we are having a completely unpolarized wave, only half of the power in that wave will be available to us. Okay? You can only get half of the power. The rest will be lost. Okay? And that's why we see that it's for communications, the wave will be polarized in many cases. We can also express P, or the power average, in that form, or the power available in that form, and we use now a factor F between 0 and 1, and we call it is the fraction of power and of AS received. That is, aperture multiplied by the power density gives us the power, and F will give us how much of that power that is being transported by the wave is received by your antenna. So F is the wave to antenna coupling factor, and is a function of the degree of polarization as well as the angle MMA. And roughly speaking, it would vary as shown with the degree of polarization, where it will go to 0 when we have complete mismatch, and will go up when we have to unity when we have perfect match between the wave and the antenna. But most of the time, we'll have only half of it when we have that value is 90 degrees. So we defined 4 new parameters, which are like the scattering parameters that you have in your ECT. We are going to call them S11, S12, and S21, S22, but we define them separately as that, where the S1, S2, and so forth come from the values, the normalized Stokes parameters that we're talking about, and we make similar definitions for the antenna, that is A11, A12, A21, and A22 for the antenna. And then we can always write that the power available from your antenna is going to be given by the S11, and is going to be given by E, the power transported by the wave, multiplied by the trace of the matrix product of A1, the antenna parameters, and the wave parameters. The trace is just the sum of the leading diagonal of the resultant matrix that will come out of this. Okay, consider the leading diagonal, give that value, and therefore we are just putting it as A11, S11 plus A22, S22, and so forth to the end. And hence, P is going to be given by that. I think this S11 is not correct there. I should be removed. I'll remove it in the things that I said. And with that, say that this, the AIJ and SIJ are what you call the consistency or coherency matrices that arise from optics. And that brings us to the end of that particular case, and we look at one thing from here. Now, this brings us to the end of that. I don't want to start any new topic now. And next week I'll be engaged in the whatever invigilation of the supplementary exams. So it's most likely I won't be available because my invigilation times are occurring on the dates that we are supposed to meet, that is Wednesday and Thursdays. So what I propose is that we have a break. Okay. So next week we are not going to meet, but you can use that time to try and see what we have already covered right now. The next topic will be the topic of wave reflection, that is propagation and behavior at boundaries. And we are going to borrow now, you can see we are just going to build on what we have already talked about. There, the concept of wave polarization is going to be very important to us because we'll now start talking about wave polarized or a wave polarized in this direction or in that other direction, impinging on a given, kind of boundary and so forth. So that's what we'll be looking at in the next, after next week. So unless you have a question, we can call it a day. I'll try and send you the slides before, after this, so that we can be seeing what it is we are expected to follow. So any question?
Yes, excuse me. Some regarding the class stream, sometimes questions are asked there. Could you, if it isn't too much of a trouble, could you please be checking, because sometimes the questions are for a few topics ago, so they would distract during the lesson.
In the chat stream?
In the class stream on Google.
As we are conducting the class, because
No, not during the class, like between
I
lessons.
can't see anything. Oh, you mean the classroom, the Google
Classroom?
Classroom?
The classroom.
That one I haven't seen any question. Have
Oh,
you sent any question?
Yes, I've asked one, but it's for a few topics ago, so it did not exactly conform with the topic being discussed.
Because what I see here is that there's someone looking for recordings.
Yes.
And I thought this one I dealt with.
There's this one for I asked on November 9th. Let me just copy paste the question.
This one I think I've already talked about the recordings. I tried to send the ones I could.
Yeah, on the notes,
but you see, it was telling me
22nd under the class comment. On the note you posted on October 22nd, under the comments, I had asked a question.
Under the comments, what was the question? You can ask it now.
Okay, let me copy it. It was regarding the there was some math you had done during the Helmholtz, when we were still covering the Helmholtz equation a while back. There was some formula which had been derived that required something like an identity of the form curl of T. Wait, let me see.
Yeah, I remember I asked you guys to prove some curls, isn't it?
Yes.
Is that what you are referring to?
No, this one wasn't among those.
The curl of A.
No, it wasn't among those ones. This one was.
So let's see. Specifically, when it comes to some calculus Daniel Helmholtz equations, there is an equation of the form h of t equal to sigma times j omega epsilon that by kc sigma plus j epsilon by kc squared cross transverse gradient of that is the equation derived from the pair del t plus the curl, which is from Ampere's law, capital law. Now, so I get this thing, the Ampere circuit law is of course the curl of H.
Yes.
And the curl of H is equal to J, which is the conduction current,
Yes.
plus the displacement current density.
Yes.
Agreed. Now,
Yes.
if the material or the medium is lossy, we can write that if the fields are also harmonic time dependent, then we can write it as sigma plus j omega epsilon.
Yes.
The j omega epsilon is the one which deals with the displacement current, because j omega is just d dt, isn't it?
Yes.
And epsilon e is just d.
Yes.
Okay. The j, we say that j was given as a convection current jv plus a conduction current j sigma, isn't it?
Yes.
And we say that we were not going to consider convection currents. You know, that movement of charges in space, we were not going to look at it. So we were just going to say that the total current that appears in ampere circuit or law is going to be given only by J sigma, which we just dropped that sigma now on it and call it J. And we call it, and you saw that J sigma is just sigma, or the conductivity multiplied by the electric field.
Yeah.
You get it?
Yes.
So the J plus d dt of d now becomes sigma plus j omega epsilon bracket multiplied by the electric field. Is that okay?
I'm sorry, you've broken a bit there. You'd say it becomes sigma plus j omega.
Okay, so write the following.
Yes.
The curl of H
Yes.
is equal to J plus d dt of d.
Yes.
You have written that.
Yes.
Now put the following. Write J equal to sigma multiplied by E.
Yes.
Then add to it epsilon multiplied by d dt of E. Because I'm writing D is equal to epsilon multiplied by E, and I'm assuming epsilon is not a time function.
Yes.
It's a scalar. So you have sigma E plus epsilon d dt of E.
Yes.
Now d dt for harmonic time dependence,
Yeah.
is j omega.
Yes.
So replace the d dt by j omega.
Yes.
You get sigma E plus j omega epsilon multiplied by E. You get it?
Yeah.
Now I can factorize that out. I can factorize E out. I just get sigma plus j omega epsilon multiplying E. And that's what we have out there.
Yeah. True.
And that is ampere circuit law.
True. And then the question is about the Kc squared.
The Kc squared,
Yes.
remember, the actual Helmholtz equation was given as, let's say for what is it called? We are splitting the del operator
Yes.
into a transverse component,
Yes.
okay, and an axial component.
True.
The K, there is a K squared that we always get, okay?
Yeah.
That is given by j omega mu, omega squared mu epsilon. That comes from the actual total derivative. Agreed?
Yeah.
So we usually say that the Laplacian of E or Laplacian of H plus K squared H equal to, okay?
Yes.
Agreed. That's what we usually say. So that K squared is a general one. Agreed.
Okay.
But then when we split this value into axial and
Transverse.
and whatever and transverse, we have said that in the z direction, the wave, the fields behave as minus gamma multiplied by z.
Yeah.
Agreed?
Yes.
So if you put it into the equations, you'll get a gamma squared. Now you get the Laplacian of E plus gamma squared plus K squared multiplied by that E. So the gamma squared plus K squared is what we are calling K squared, KC.
Oh.
Okay?
Yeah.
It's a characteristic of that medium and the shape of the region which the wave is propagating through.
Oh, okay. Thank you.
Yeah. The KC comes just because we have split the whatevers, the fields into axial and transverse components.
Oh, thank you.
Okay, you're welcome. So this general, what more general thing are you looking for?
You've responded to it. You've responded to it.
Okay, fine. So usually it's better to use the del operators the way they are, because we'll see that when we start having symmetry in axial symmetry, like cylindrical or rectangular, the del operator has to be replaced by its components. And that's why it's important that you use them. For now, you use them the way they are. But when we get the particular coordinate system, you replace it with a complete with the actual coordinate system that will be dealing with. So with that, anybody else with a question? So since you are all quiet, then I'll take this opportunity and wish you a nice weekend and a good holiday. Try and use the holiday responsibly. Don't go spreading the virus.
Thank you.
Good day and thank you. And thank you for the persevering yesterday.